So our next goal will be to simplify maps into CW complexes, between CW complexes, and so on. And simplifying here means you're changing up to homotopy, and the image of the map has certain control. Okay, it's going to avoid most cells. It's going to be in finite dimensions, and so on. And we can have more concrete control over that. Okay. To start with, we'll see a relatively easy result. So let's take X to be a CW complex. Okay. And we take K to be compact, just an abstract topological space, and F mapping K to X. Okay. Then the theorem here is that there exists G mapping K to X, which is homotopic to F, such that if I look at the image of G and look at all those, so it would be better to quantify it the other way, such that if I look at all alpha in AN, such that, well, for some n greater than or equal to 0, with the image of K intersecting the interior, I was going to write that, so more precise way of writing it is phi alpha of D naught n. So the image of the interior, which remember is mapped up open such that this set is finite. In more informal terms, if you have a compact set up to homotopy, you intersect only finitely many cells in their interior. So you are contained in, equivalently, you are contained in the union of finitely many sets, because you can avoid the sets whose interior. You are contained in the union of all the cells. So you just look at those whose interior you intersect, and you will be contained in their union. Okay, because the boundary is already contained in a lower skeleton. Yeah. Okay. So first we'll just obvious bit of set topology is f of k is compact, since k is compact. But this gives nothing about the CW complex. Crucial point is we can look at the midpoint. Okay, so let mu alpha equals phi alpha of the point 0 in Dn. The origin, the 0 vector if you wish, in Dn, where again n is greater than or equal to 0 and alpha is in An. So the interior of some cell. So these are the midpoints. Okay, and the following, which I'll leave as an exercise, which is quite easy, is that the set of all mu alpha, okay, so alpha in An, it would be better to write union of An's alpha some index, is a discrete set. Okay, so we had some 1 cells here, and then they're forming our space. I'm drawing them embedded. That's a bit misleading, but still, if I had a 2 set like this, I'm saying if I took these midpoints, which I will color in purple, as well as of course midpoints of the 0 cells, and the midpoint of this guy, etc., then I can find neighborhoods of these, little orange neighborhoods of these. Okay, the attaching map may cross this several times, so you would have to find appropriate neighborhoods, but that's essentially just saying that you can do this. Is just saying that the space topology on the boundary is the subspace topology. We find little neighborhoods of all these guys. So there were more midpoints on these sides which I have ignored, so we can actually have to take some more neighborhoods which are all disjoint, and they are all open sets. So this is a discrete set. Yeah, so formally is not difficult, but I will leave that as an exercise. So great. So what does this tell you? So this tells you crucially that hence K intersection, let's give this a name, M for midpoints, M is finite, because a compact, not K, but GF of K intersection M is finite, because this is a compact set. Okay, so it intersects the midpoints of only finitely many sets, and then if f of k, let me call this mu alpha, if mu alpha is not in f of k, okay, we can homotop f to be disjoint from from the interior of the whole cell alpha, phi alpha of D0. And of course you know this very well. Yeah, so this is just the radial homotopy. I have a cell. I'm drawing it wiggly because it need not be round in the image. In fact, there may be identifications on the boundary. I have its midpoint, which is this purple point, and I have F, which is, well, it's something. I'll pretend it's one-dimensional here. It misses the midpoint, and if it misses the midpoint, then I simply radially homotop it away from these cells. Of course, you have to put together the radial homotopies. There are various ways in which you can do it. So you can radially homotop it so that it goes into the boundary of this guy. It's in the not in the interior anymore. Okay, so using radial homotopies with time, with respect to all the midpoints, you can push it off the cells which it intersects. Okay, so this is all. This was the first simple argument. It tells you that if I took a compact set, okay, and I can homotop it so that it is disjoint from all but finitely many cells. In fact, all cells whose midpoints it's disjoint from. Okay, we want to refine this eventually, where we have dimensions. That's a little bit of a more complicated argument. But for now, let's just look at note this result.